All right, good afternoon. You look bored. I want to tell you something interesting. So 50 years ago, almost exactly 50 years ago, Feynman gave a special lecture on the principle of least action on precisely this topic to undergraduates at Caltech, sophomores, I think. So today I shall try to do something broadly similar, but I will be a little bit more ambitious because 50 years on, students are more advanced, and I think I can cover a much wider field. I'm prompted to give this lecture because over the last few months, quite a number of students have come to ask me questions on broadly the more elegant or formalistic side of physics. I have tried to answer the questions, but I thought I would do something more systematic and do it for more students. And I know at least the freshmen finish the exams this morning, so this may be a good time. But before I actually start into the substance, a word of caution. This lecture is about mechanics about 300 years after Newton, about electromagnetism about 150 years after Faraday and Maxwell, about special relativity just over 100 years after Einstein, about quantum mechanics in round numbers also 100 years after Bohr, Heisenberg, and Schrödinger. So with the long period of time, the ideas have matured and our understanding has deepened. So we are now able to understand and to express theoretical physics in ways that are extremely elegant and almost breathtaking. It is like a fine wine made mellow with age. But when these ideas first saw the light of day, when they were first invented, when they were first discovered, they were messy, confusing, inelegant, incoherent, disorganized, even sometimes self-contradictory. If you think about, for example, the Bohr model, it's not really consistent. It is like making wine by stamping on the grapes with your bare feet. You have seen people make wine that way. That's how wine is made in a messy process, but 100 years later it becomes a wonderful mellow wine. And I say this because if you are captivated only by the elegant and the formalistic side of physics, the best that you can achieve is that you will become an A+ student. You will not become a physicist engaged in the process of creation. So the word of warning is not to let this lecture drive you only into this little corner of physics. You must develop an interest, a liking, and skills for the more messy side of physics if you ever want to participate in the process of creating new physics, doing research. Pursuit of elegant, overarching ideas is sometimes called the Cartesian approach to science. Top-down, formalism, elegance. The opposite approach, bottom-up, looking at phenomena messy as they are, is sometimes called the Baconian approach to physics. Both are, of course, necessary. Today, I only show you an example of the former, the Cartesian approach, but I think we need to involve both approaches if science is to progress. So, with that preamble, let's start with a very simple problem in Newtonian physics. So let's consider an experiment. High school physics, all right? I throw a stone upwards, and it's forced back to the ground in a time capital T. I take my x-axis upwards, and I want to ask what is the trajectory like. So I'm looking at a position time graph. I know that the motion started off at x equal to 0 at time t equals 0. And I also know that it ends at time capital T back on the ground. Right? That's what I know. Now, even a high school student will know what the solution is, right? So some parabola. Okay? And if you write it down, it goes like this, that the correct solution is 1/2 g, the time, and capital T minus time. You recognize by inspection that is correct because it satisfies both conditions at the initial time and the final time. Now today, departing from what you usually do, I'm not going to give you two initial conditions. I'm going to give you one initial condition and one final condition. And I ask, of all possible paths that you can draw connecting these 2 points, not just the correct path, but maybe an incorrect path. For example, that one. That's incorrect. Maybe a nearby incorrect one. That's incorrect. How do you decide which one is correct and which one is incorrect? That is the fundamental question in Newtonian physics, and Newton gave us the answer, right? And the answer in this particular example is that you check the following. In this case, you easily find that x double dot is equal to minus g. So if it satisfies that equation, that's the correct trajectory, the correct path. More generally, of course, Newton tells us to check whether a path that somebody puts up is correct. You check whether this condition is satisfied, right? V is the potential energy. So if somebody draws an arbitrary path and asks you whether this is the right answer, you subject it to that test, which is basically Newton's second law. That's really all of Newtonian physics in one nutshell, right? I will be talking about the simple case of one particle in one dimension, but it's easy to generalize to 3 dimensions to many particles. Same idea. That you have learned. Today, I'm going to tell you a different approach to this problem. If somebody gives you a path, what do I mean by a path? Any one of these is a path, not necessarily the correct one, all right? A path is a function x of t. And I will always pay attention to paths that start and end at the given points, as I have drawn here. Somebody gives you a path. Now I will give you an alternate prescription to determine which is the correct one. And the prescription goes like this. It tells you that for any path, which I write as a function. Now, when I write this, I don't mean the value of x at the time t. I mean the whole function x of t. Think of it as a way of denoting a curve. For every function, I will calculate a real number, which I call s, right? It's called the action. So for any curve, I will tell you a way to calculate a number. So for example, for the black curve, you find the number is 3. For the next curve, the neighboring curve, you find it's 3.1. For that one, you find it's 4, and so on. Right? Then the prescription is the path with the minimum s is the correct path. Right? So that is the prescription, and it's called the principle of least action. That's not saying very much so far. I have to tell you a rule for calculating, for expressing s. The rule goes as the following. That the action for the whole path consists of the sum of the action for each segment. All right? So you calculate the action for each short segment and you add them up. And the action for each short segment depends only on 2 things. A short segment is just a short straight line. To specify that straight line, I need to know the value of x and I need to know the slope. Right? So it's a straight line like this. So the action is the sum over all these segments. And of course, the action for each segment is proportional to the size of that segment. So I can write that as something proportional to delta t. Delta t is the time involved in that segment. And this object, which is basically the action per unit time, is called the Lagrangian. All right? So if I take the continuous limit, that means the action is the Lagrangian dt between, now I will generalize, not necessarily between 0 and capital T, but any t1 to t2, the initial times. Right? And the Lagrangian, as I said, in general is a function of x and x dot. And very often, I will write x dot also as the velocity v. I still haven't said very much, except the form of the Lagrangian. Now I will tell you, just by telling you the answer, what the Lagrangian is. And I'm sure you all know, it is actually the kinetic energy minus the potential energy. For those of you who are seeing this for the first time, you may be surprised by the minus sign, right? Because you're all used to the energy having the plus sign. Now, how do I know that? I have given you a rule, right? So if I draw any curve, by executing this rule, you put this in, you calculate, you get a number. You calculate this for every possible curve that you can imagine, then pick the one with the smallest s. I claim that's the right answer. How do I know that's the right answer? In other words, I now want to prove to you that this prescription is equivalent to Newton's law. Okay? Now, that's not so difficult. You know, normally when you have a function and you say you are at a minimum, in fact, at any extremum, what happens is that if I make a tiny displacement, I change the argument by a small bit, say eta, to first order in eta, the function does not change. So the first order variation is 0, right? So I will impose this condition, and I write it in the following way. The variation in S, by which I mean S calculated for a small change in the argument. Now the argument is not a number, it's a function, and eta is a function of time that tells you the difference between a curve and a neighboring curve that differs by eta. All right? The difference is a function of time. So this minus the original one, that's what I mean by the variation, and I always understand this to mean to first order in eta, that has to be 0. Okay? So let's just put it in. So what do we have? I have the integral of, for this one, 1/2 m x dot plus eta dot squared minus v at x plus eta, and then minus 1/2 m x dot squared plus v of x, all integrated. All right? So, just expand. The terms without eta will cancel. Then the terms linear in eta gives me m x dot eta dot from this cross term. And then if I do a Taylor series expansion on this guy, the term I get is minus dv dx times eta. Is that okay? So you have a term proportional to eta dot and a term proportional to eta. Now, eta and eta dot, if I look at one time, they are independent. Because if I choose any function, I can specify its value at the point and its derivative, right? But if I look at all times, they are not independent. Because if I specify eta at all times, then eta dot is totally determined. Okay? So the two terms are not independent, and I want to do something to express everything in terms of eta. And the rule is actually very simple. It's the rule of integration by parts. So let me be general. So suppose I have a function a times b. I take its derivative. This is, of course, a dot b plus b dot a. Suppose I integrate this now from t1 to t2. So I integrate this. This is easy. The integral of a derivative, that gives me ab at the two extremes. If I now take a special case where at least one of the factors a and b vanishes at the endpoints, Okay? Then the left-hand side is 0. And on the right-hand side, I have a rule which I can write symbolically as the following, that whenever I see A dot B, I can change it to minus B dot A, with the understanding that everything is under the integral sign. Okay, so that's just integration by parts, where the endpoints vanish. Okay? That's the case here, because if I look at one of the factors to be eta, eta vanishes at the endpoints, because I am comparing paths that agree at the endpoints. So the difference between two paths is 0 at the endpoints. That's why I can do this. So I will be, see, when you've done this a million times, it's very simple. All you need to do is the following: erase that dot, move it here, and put a minus sign. Okay? Whenever you do these minimum principles, you integrate by parts, you do this trick every day. Okay? Now, both terms are proportional to eta, so I can pull this out, right? So I can pull the eta outside the bracket. And now, oops, I emphasize the fact that it is a function of t. So the curly brackets is a function of t. That function of t multiplied by an arbitrary function, eta of t, and integrated gives 0. I can in particular choose eta of t to be 0 everywhere except a tiny bump at, say, t equals 5. Then that picks out the value of the braces at t equals 5. It has to be 0, right? So the curly bracket has to be identically equal to 0 for all t. But that's just Newton's second law, right? So I have proved the equivalence of this principle to the Newton's second law that you are familiar with. Easy, right? Okay. But if you think about it, it sounds a little bit strange. Because imagine, let me see, I just draw it again. So this is the correct path, and this is an incorrect path. Think about two stones that are moving up. One of them does not obey the law of physics, all right? Just imagine. So the first guy goes up like this, the second guy goes up like this. And you ask them, which one of you is on the right path? Which one of you is doing something proper? According to the principle of least action, I can't answer yet, because I don't know how to calculate the action until I've completed the journey, right? So you don't know, the stone doesn't know how to take the next step in the correct way until it has finished the journey. Sounds strange, right? Because normally when you solve a differential equation, the way it's expressed as Newton's second law, you do it one step at a time, right? I think I taught most of you first year physics, and you all know how you can convert a differential equation to a difference equation. You know the initial position, the initial velocity. Newton's law tells you the acceleration. With the acceleration, you can calculate the velocity 1 microsecond later, right? So if you have the velocity 1 microsecond later, so over that tiny interval, you have the initial velocity, the final velocity, you know how much the particle has moved. You find a new x. So you get x and v 1 microsecond later. And you take one step at a time going forward. So it's one step at a time, differential in t. But now I have given you a prescription that is global in t. You can't say which one is correct until the whole journey is finished. Sounds weird. The answer to this paradox is actually you can give it at two levels. At a formal level, it's not weird because I've shown the two are mathematically equivalent. So I need to give you a heuristic answer a little bit later. Okay? Any questions so far? All right. Now, if they are equivalent, why should I invent, or why should Lagrange and Hamilton and so on, why should they invent this new way of doing things, except to make life difficult for sophomores studying physics? What good is it? Why is it better? I will tell you several examples to show why it is better. The first, you actually know very well. You see, you have this law, mx double dot is minus dv dx. And of course, if you have more than one dimension, you have my double dot is minus dv dy. But suppose I use polar coordinates, say r and phi, okay, 2 dimensions. Let's keep things simple. Would you be able to say that mr double dot is minus dv dr? Is that correct? Even a high school student knows that it is not correct because there is the centrifugal force, right? mr phi dot square, right? That's a centrifugal pseudo-force. You learned it in various ways. Even in high school, you call it mv square over r or whatever, right? Or m omega square r. Omega is phi dot, right? This simple example shows that if you write it in the normal Newtonian form, you are confined to Cartesian coordinates. If you go to any other coordinate, the law of motion takes a different form. And you don't know what that different form would be without writing out a lot of details, right? But the principle of least action is the same in any coordinates, because I'm telling you it's the time integral of the kinetic energy minus the potential energy. When I say kinetic energy, did I say I calculated in Cartesian coordinates? When I say potential energy, did I say I calculated in Cartesian coordinates? So the principle of least action works in any coordinates. That's the first advantage. And I will now show you how this works out in this case. To anticipate this, let me do something a little bit more general. The coordinates I will call Q, which actually is, you can think of as Q1 up to Q capital N. So say Q1, Q2 would be R and phi, okay? And the Lagrangian is an arbitrary function of Q and Q dot. I'll be schematic. Think of there's only one Q, but you can easily add a subscript. So what do we have? Oh, one other thing. To change notation, this little change in x, which I call eta, henceforth I will call delta x, because there will be lots of different things I want to change, right? The change in x I call delta x, the change in y I call delta y, and so on. So if L is a function of Q and Q dot, then the change in action is the change in L integrated, right? And how does L change? Well, it is because Q has changed by delta Q, and because Q dot has changed by delta Q dot, right? The change in a function of two variables, the first argument changed by delta Q, the second argument changes by delta Q dot. All right? Now, using the standard trick, and I will leave it to you to check that the boundary condition is satisfied, I erase that dot, I change that minus sign, and I put the time derivative on the other factor, right? If you are familiar with this, it takes only a second, right? Move the time derivative from one factor to the other factor and change the sign. Now I can move delta Q to the outside, and it's arbitrary. So what's left inside the square bracket must be identically equal to 0. So I get the equation of motion that the time derivative of dl dq dot is equal to dl dq. That is the Euler-Lagrange equation of motion. And if you have a number of different variables, then that holds for each variable. Okay? And I didn't say how L depends on Q and Q dot. It's not necessarily 1/2 mq dot squared, for example. Okay? Usually we give this a name. This guy we call the corresponding momentum. It's a momentum in a generalized sense. It's called the canonical momentum. All right? So this equation is sometimes also written as d dt of Pn is the change of L with respect to Qn. That's the Euler-Lagrange equation of motion. Let's go back to circular motion and see how that works out. Well, what is the Lagrangian? It's the kinetic energy. So in circular motion, the kinetic energy is what? Right? That's the kinetic energy. And let me keep things simple and take the potential energy to be purely radial. Does not depend on phi. You can take it more general to depend on phi. So let's take the R equation. So what is PR? PR is dl dr dot. That's easy. That's m r dot. That's what you expect, right? Now I apply the Euler-Lagrange equation, which tells me that its time rate of change, which is mr double dot, is equal to dl dr. Right? That's the rule. So what is this? So I differentiate this with respect to r. So first I differentiate this term. I get the negative gradient of the potential. But there is another r here. So I differentiate this. I get plus mr phi dot squared. Centrifugal force comes out without having to draw any single diagram. Right? Pops out automatically. You just grind the algebra. You don't have to think. You don't have to draw diagrams. And the reason is, if you go to coordinates that are more complicated than polar, totally arbitrary curvilinear coordinates, how can you ever deduce anything by simply drawing diagrams? Right? So that is at least one example where this alternate formulation gives you an advantage. All right? So going to generalized coordinates. Secondly, I will now teach you special relativity in 5 minutes. Now, normally, suppose I have 1 point here and 1 point there. The 2 points would have a certain separation in x, a certain separation in y, and a certain separation in z between the 2 points. What is delta x, what is delta y, and what is delta z depends on how you orient your coordinates, right? If I take my axis this way, I get 3 numbers. I take my axis this way, I get 3 different numbers. But there is a combination that is independent of how you choose your axis. And of course, we all know Pythagoras' theorem tells you that you take that combination, then whether you take your axis this way or that way is the same answer. Now, in special relativity, we are talking about events. Say this, something that happens here and at this time, and this, something that happens there and at that time. In special relativity, of course, then that there is also a delta t. By the way, I will use units where the speed of light is 1, c is equal to 1. The whole essence of special relativity is that this combination is the same according to every coordinate, according to every observer. Okay? It's sort of like a generalized Pythagoras theorem in 4 dimensions, time being the 4th dimension, but coming into Pythagoras theorem with a minus sign. So that is what we call a relativistic invariant. It's the same number that you get according to every observer. And the point is, suppose I'm talking about a free particle moving in space. I want to construct an action, capital S, that also is an invariant. Now, why? Why do I want the action to be an invariant? Suppose this hypothetical motion or path, I call that A, path A, and that I call path B. If everyone agrees that path A has an action of 3 units and path B has an action of 4 units, let's say, then when the 2 observers each chooses the minimum action, they would both choose A, right? They would arrive at the same final answer. Therefore, physics will be invariant, that every observer will determine the same solution. So I will be able to satisfy what is called the principle of relativity, meaning that what is the correct solution, what is the correct motion, you must get the same answer by every observer, if I do so by choosing an action that is an invariant. Therefore, I now want to write down an action which is an invariant. There is basically only one thing I can write down, right? That's the only invariant you have for each small section of the motion. Okay, so I have to start with something like this to construct an invariant for a short interval, for a short part of the motion. Is that okay? And then I add it up for the whole path. See, there's nothing else you can do. That's the whole point. Can I simply add up these things? I take the action delta capital S to be this. Why? Yeah, this is quadratic in the size of the interval. So if I imagine chopping each interval into 2, then this becomes 1/4, and I have 2 terms, right? Okay? So adding up the 2 terms for the 2 halves, I get 1/2 the original answer, 2 times 1/4. Which means it would not converge as the size of the interval shrinks to 0, right? You always think about taking the limit. So you must somehow take the square root of this. Okay? If you take the square root of this, or something like the square root, then if I chop it into 2, each part is 1/2. And then I add the 2 bits together, I get the same answer as before. So it converges as the size of the interval shrinks to 0. So I want to take the square root. Can I take the square root of this? Now, you are thinking about a particle that has moved through a certain spatial displacement delta x, delta y, delta z in a certain time delta t. Of these terms and this term, which one is larger? Suppose you are talking about 1 year, delta t is 1 year, the distance traveled must be less than 1 light year, right? So the spatial terms together must be smaller than the t term. So this, as written, will be negative. Okay? I can't take the square root. Easy enough, I turn it around. Okay? So the action for a small part of the motion must go like this: delta t squared minus delta x squared minus delta y squared minus delta z squared. I take the square root. And who's to prevent me from multiplying by a constant? That's the only thing you can write down, right? There is nothing else you can write down that satisfies the general principle that I have described. Okay? Now, how do I deal with this? Well, easy enough. I pick out a factor delta t. What's left inside the square root is 1 minus what? Delta x over delta t squared, delta y over delta t squared, delta z over delta t squared, and that is the velocity squared. Right? Are you with me? Not going too fast? But I told you earlier that the action per unit time is a Lagrangian. So I have found the Lagrangian for a free particle. It is some constant 1 minus v squared. All right? How do I determine that constant? Actually, it doesn't really matter. It's a matter of convention only. Because if you err by a factor in the Lagrangian and therefore the action, when you minimize, it's the same solution, right? But just to follow convention, let's choose the right constant. Let me look at the case where the velocity is small. When I say small, of course, I mean compared to the velocity of light. So I can expand this. So this goes as k, 1 minus 1/2 v squared. The first term doesn't matter. It's a constant. It's an additive constant. If I add a constant to the Lagrangian, I add a constant to the action. That does not affect the process of minimization, right? Like you have a function, I add a constant to the whole function, the minimum is still the minimum. So what matters is the second term. And I know for a free particle that's moving at slow velocities, Newton tells me that the Lagrangian is what? It's the kinetic energy, 1/2 mv squared. So I'm now able to identify k is minus m. All right? So therefore, I get the answer. That is the Lagrangian for a relativistic free particle. You may have seen this formula before, but it looks a bit strange. You have seen that square root in the denominator lots of times, right? In the numerator, it seems a bit strange, but remember, it just comes from this. I have told you a rule. What is the momentum? If you know the velocity in terms of the velocity. So the momentum is dl, the velocity, right? And I won't do the algebra, all right? If you do the algebra, it's mv over the square root. That is, of course, the relativistic momentum. How did you learn this formula? Huh? Proper time and so on, right? But now it just comes out like this. If you have the idea of an action of a Lagrangian and you use the fact that things have to be invariant. Oh, I forgot one thing. Having derived the Lagrangian equation of motion, let me also tell you the Hamiltonian. Now, the Lagrangian depends on Q and Q dot. So if I change Q and Q dot, I get the L dQ, the change in Q, plus dl dq dot, the change in q dot. Right? But the second term is actually P. That's the equation of motion. That's the definition of P. P is the change of L with respect to Q dot. So that's a nice formula that tells me how things depend on Q and Q dot, right? If I tell you Q has changed by this much, Q dot has changed by this much, that's a good way of finding out how Lagrangian has changed. So if position and velocity are your independent variables, this is a nice thing. But suppose I want position and momentum to be my variables. What do? Let me call this Q dot, let me call that V for a moment. Right? Velocity, okay? Q dot is just a velocity. This is a standard trick called a Legendre transformation, because if I want to get rid of the P dV, I do the following. If I look at the product PV, then I have a term which is P dV and a term which is V dP, right? Now I take the difference between these two equations. I find that the change in PV minus the Lagrangian, then this cancels. What I have is that one first, V dP minus dL dq dq. All right? One more line. V, remember, is Q dot. And dL dq is what? P dot. Right? So this is minus right? Is that okay? Did I go for minus sign? Yeah, correct. I now define this quantity, give it a name. It's called the Hamiltonian. The Hamiltonian is a nice quantity when you want to use independent variables which are Q and P. If I change Q a little bit, I know how much H changes. If I change P a little bit, I know how much H changes. The Hamiltonian is actually the energy. It's actually a conserved quantity, which is the energy, for the following reason. Let me try to write this in a slightly better way. That I can write as the partial derivative of H with respect to Q is this, right? Is minus P dot. And the partial derivative of H with respect to P is Q dot. Okay? You can think of this pair of equations as two first-order equations that tell you how Q and P change in time. If I give you H, you know Q and P at this time, then this tells you what is Q dot, and therefore what is Q a bit later. It tells you P dot, and therefore it tells you what is P a bit later. So those are the Hamilton equations of motion. Now it's easy to show that H is a conserved quantity if H does not have an explicit time dependence. How does that go? It's easy. Because H is a function of Q and P, and Q and P are functions of time. So the rate of change of this guy is, of course, obtained by the chain rule, dH dq q dot plus dH dP p dot, right? But I have just given you dH dq. What is the first factor? dH dq is minus p dot. And this one, dH dP, is q dot. So conservation of energy for any form of Lagrangian comes out automatically. Okay? Now, coming back to the relativity. What is the Hamiltonian, or the energy? It is Vp minus the Lagrangian. I have already found P, which is mv divided by the square root, minus the Lagrangian is m times the square root. Do some algebra, what you find is that the energy is m divided by the square root. Okay? So the last step is just some simple algebra. You can I think you can see it, right? You put everything on this denominator. So this is mv squared. And over here you have 1 minus v squared. So the v squared cancel, you're left with a 1. You put back factors of c to get it back to conventional units. That's the formula for the relativistic energy. And in particular, when the particle is not moving, what is the energy? mc squared. So E equals mc squared drops out like this. All right? And that's why we have electricity from Diabe. E equals mc squared. That's why we have energy from the sun. E equals mc squared, all dropping out from this formula. Okay? And you see, everything comes out so naturally if you use the action formalism rather than worrying about forces and so on. Okay, so let's see what's next. Okay, next, very quickly about electromagnetism. Just to tell you that the simple form of the Newtonian laws of physics, that mx double dot is minus the gradient of the potential energy, right? That doesn't work when there is a magnetic field. Why? Suppose I turn on the magnetic field. Does it change the potential energy? If you express your mechanics, your dynamics, only in terms of the kinetic energy and the potential energy, there is no way to describe the effect of a magnetic field. Magnetic field does not change the potential energy. It does not do any work. So the simple Newtonian form that I started off with is going to be dead when you talk about magnetism. So how do you do it? I will just quickly tell you what the trick is. Suppose you have just the electric field. And let me talk about a particle that's moving slowly. So it's 1/2 mv squared minus, no. Let me look at the action, not the Lagrangian. Right? The second term, Q times phi, the scalar potential, is the potential energy. So that's the usual form, kinetic energy minus potential energy. Now in relativity, what you have, as I told you earlier, is dx, dy, dz, and also dt. And if you take dot products in the usual way with 4 vectors, you get an invariant. And what happens here is that phi is like the time component of a 4 vector, and the vector potential that you are familiar with are the spatial components. So if I add this term, that is like, apart from the factor of Q, taking a dot product between these two, with the opposite sign for the time term. that will give you something that is relativistically invariant. It's the same for every observer. And that will give you correct relativistic physics. Now, but that doesn't look like a Lagrangian. So the way to do it is divide by dt and multiply by dt. Now, if I peel off the time integral, the rest is a Lagrangian. Okay? So the Lagrangian in the presence of a vector potential is the kinetic energy minus q phi plus q v dot a. Okay, this is v. If you write this down and you pop it into the Euler-Lagrange equation of motion, you get Lorentz force law. I won't do the arithmetic. It's a little bit tricky. It's a little bit tricky. If you do it yourself, you probably get it wrong the first time. Okay, but it's only arithmetic subtlety, no physical conceptual subtlety. Okay, so again, just using the idea of invariance, you get magnetism straight away. Okay, so the link to quantum mechanics. Yes, that's important. You have all learned about plane waves. So for a plane wave, you write something like this, right? Kx minus omega t. Let's say propagating only in the x direction. You know what these symbols mean, right? K is the wave number and so on. In quantum mechanics, we have complex wave functions. So a plane wave in quantum mechanics looks like this. That's something that you are also familiar with. So I write this as e to the I times the phase. So the phase is k times x minus omega times t, right? Easy enough. Now, you all learned in modern physics that k is the momentum divided by h bar, right? That's de Broglie. You usually write it in terms of lambda and so on, right? And omega is the energy divided by h bar, or the Hamiltonian divided by h bar. So I have phi is then 1 over h bar p times x minus Hamiltonian times t. Right? But that is only true for a plane wave. A plane wave is a wave where the wave number, the momentum, the energy are constants. What if the wave number is changing? The wavelength is changing. Easy enough. You chop it up into little bits. For each bit, the wave number and so on is constant. So for each part of the motion, the increment in the phase is p delta x minus h delta t, because for a short part of the motion, it's a plane wave. Now I pull out a factor of delta t. What do I have? P times, what's here? V minus h. Right? Simple algebra, right? What do you recognize? What's this? It's a Lagrangian. Now, I'm sure you all know about this combination. Most of you all know about this combination being equal to L. Right? You have all learned Lagrangian mechanics. But I bet most of you did not realize that those two relationships are the same thing. So what I have found, if I now add everything up, the total phase is the sum of these, so it's the integral of this. So I find that the wave function goes as e to the I. So when you integrate, what do you get? You get the action, right? So quantum mechanical wave functions go as e to the I action over h bar. That is how you go from classical mechanics to quantum mechanics. All right? Easy enough, right? Nothing fancy here. No complicated mathematics. Is that okay? All right, so I think I will, for the moment, skip topic 11. I will instead, let me see, 10 and 11. Okay. Let me say a little bit about now I want to do it backwards to give you a heuristic description of how to go from quantum mechanics back to the classical limit if h bar is small. Suppose I want to go from this point to this point. I can imagine going along any path. Say that is the classically correct path. That is a classically incorrect path, all right? Maybe I use a different color. This one does not satisfy Newton's law, the blue one. But if you look at the quantum prescription, the two paths have different phases, but the magnitudes are the same. It's e to the I, a real number. So the probability of both paths are the same. The correct path and any incorrect path in the same sense, in some sense, are equally likely. That's weird. But if you are looking at a classical system, that means you are not looking very closely. You are not doing fine resolutions. So when you say a classical path, actually you are thinking about a bundle of paths around this line and a bundle of paths around that line, which you can't distinguish. It's like a tube, okay? You have a coarse grain. You are not wearing your glasses. You can't see too closely. Now, you see, if I look at a path that is not classically correct, then the neighboring path would have a different S, right? The phase is S over h bar. So if S differs by a little, because h bar is so small, the phase differs by a lot. So if I look at an incorrect classical path, all the neighboring paths have totally different phases. And when you add them all up, like when you do interference calculations, the answer is basically 0. Okay? So if the path you have chosen is not a minimum of S, then adding up a bunch of neighboring paths will give you destructive interference and therefore basically 0. And this statement is true in the limit h bar going to 0. Whereas for the correct path, if I deviate a little bit, S does not change, right? Because it's minimum S. So I deviate a little bit, S does not change. So all the neighboring paths have the same phase. You add it up, it's constructive interference. So if I'm talking not about a single line, but about a tube of paths, this one basically disappears. And what you observe is that it goes only along that bundle of paths. And that is how you go from quantum mechanics back to classical physics. Okay? And this idea, actually, you have seen before in Fermat's principle about light propagation. You have all learned this, so I won't spend time on it. It says that the law of optical propagation is minimum time from A to B. And that single statement actually includes three laws of optics: straight line propagation in one medium, law of reflection when a ray of light hits a plane surface, and Snell's law when it goes from one medium to another medium, where the speed of light is c over n1 and c over n2. You all know how to do that geometry, right? And the idea is the same. Actually, light is governed by Maxwell's equations, waves, and the Fermat's principle just counts that constructive and destructive interference in exactly the same sense. One other thing, just to give you a taste of another example where minimum principles are useful. And I take the example of electrostatics. You see, in electrostatics, you are often asked to solve a problem such as this. You want to find a potential such that this satisfies Laplace equation inside a certain volume, subject to the boundary condition that this is given for the surface, which is the boundary of V. Okay? So on this surface, I tell you what the potential is like. I tell you it satisfies Laplace equation inside, and I ask you to find the solution. You have all encountered this kind of problems, right? How do you even know that there is a solution? Well, I'm going to reformulate it in terms of a minimum principle. And although normally people don't do so, I call this the action. The action is I tell you the action is 1/2 gradient of phi square volume integral. So you choose any phi that satisfies the boundary condition. Okay? Having chosen a phi of the position, you calculate this object. Choose the one that gives you minimum s. I claim that's the correct answer. Same flavor as the principle of least action, right? Now, let's see why it works. If it's minimum, then it has 0 variation. And the variation is gradient of phi times gradient of delta phi. All right? Standard trick. Move this derivative over to this one with a minus sign. Right? Integrate by parts, because delta phi vanishes on the boundary. So I have done an integration by parts. And I'm saying this is 0 for any function delta phi, therefore this is 0. So I can reformulate Laplace's equation by this minimum principle. That serves two functions. One, it actually gives you a number of approximate methods for finding the solution. Let's set that aside. At least it gives you immediately a proof that a solution exists. Because you choose all possible phi. The s must be positive, right? If you have a bunch of positive numbers, there must be a minimum. A minimum exists, so a solution exists. Okay? So very often when you want to prove the existence of solution of partial differential equations of a certain class, a minimum principle is very often a very convenient tool for the proof. All right, final 15 minutes. I want to derive Schrödinger's equation. What is the fundamental question in quantum mechanics? It is, if I give you the wave function at time t equals 0, I ask you to find the wave function at time t. Right? If you know how to do this, you understand quantum mechanics. The first statement is that the two must be linearly related. Suppose you have two vectors which are linearly related, then you say AI must be equal to Gij Bj. Right? If A and B are vectors, and if you say they are linearly related, that's the most general way of writing it. But if the functions are described not by discrete variables, but by continuous variables, it's the same idea. If you have A, which is a function of x, depending on B, which is a function of x prime, then you have a G x prime, sum over x prime, right? But if x prime is a continuous variable, you would write this as an integral of G x prime B of x prime. That's not saying anything. That's just saying that they are linearly related. That has no dynamical content, all right? So the wave function at a later time and the wave function at an initial time must be related by some object G. Okay? And that object G must depend on T. So for whatever T, that's how it goes. Again, not saying very much until I tell you what is G, right? Just saying they are linearly related. Okay? G is called the propagator. It tells you how the wave function propagates from x prime to x. Now, from now on, I will talk about the case where t goes to 0. Very small t. Because if I can answer this question for very small t, I know the wave function 1 microsecond later. Then I can do it 1,000,000 times. Then I will know what's the wave function 1 second later, right? So if I know the answer for very small t, or in other words, to first order in t, that's good enough. So henceforth, t will be small, calculated to first order. So what is G? Let me draw a picture. T-axis. So this is psi of x prime, 0, psi of x t. G tells you how the particle propagates from x prime to x in a time t. All right? And I now tell you the answer. In fact, you already know the answer. The answer is, the G is e to the is divided by h bar. Psi of x prime and 0 dx prime. That is the rule. The function g is just e to the is over h bar, because that is what I said earlier is the wave propagation from here to here. Well, not quite. I have to multiply by a suitable normalization constant, because I have to make sure that if I start off with a normalized wave function, I end up with a normalized wave function. That just means probability is equal to 1. So let's calculate this. So that's this factor, e to the I. What is the action? Well, it's the kinetic energy right? That's the kinetic energy going from here to here, minus the potential energy times time. Is that okay? I missed an h bar. Yeah. I have cheated a little bit because the potential energy, who said is to be evaluated at x and not x prime or halfway in between. But these 2 points are very close. And this thing is multiplied by t, which is very small. So it doesn't matter. Right? Now you can be more formal, but that's correct. Here, I cannot say x and x prime are very close because it's divided by a very small quantity. Right? So let's do that integral. So what I have is that psi at the later time is given by an integral. And let me call x prime minus x, let me call that u. It is then e to the I m over 1t h bar u square e to the minus v of x t over h bar I psi of x plus u 0 du. Is that okay? Are you with me? I just call x minus x prime, I call that u. That's all I have done. Now, this does not depend on u, so I can bring it out. And the rest I write in the following way. E to the minus I v of x t over h bar times normalizing factor e to the u square minus u square over epsilon psi of x plus u 0 du, where epsilon is actually a complex number, but a tiny complex number. It is t h bar over, now I goofed in 2, there's a 2 here, m over 2. T h bar, 2 t h bar over I m. Okay? And this is a very small quantity. Small because t is small, not because h bar is small. I'm doing quantum mechanics. I don't assume h bar is small. Is that okay? Now, let's look at that integral. In fact, I will look at a more general integral, which goes like this, that you have e to the minus u square over epsilon, some function of u du. And I want to look at this when epsilon is very small. Now, this is actually a product of two functions. One is the Gaussian. The other is f of u. This is the Gaussian. Right? It's the product of two functions. But as far as this function is concerned, this function, I only need to know it in this neighborhood, right? Because the Gaussian is very narrow. When I go beyond that neighborhood, the function f is multiplied by something that's almost 0. So I am entitled to expand this as f of 0 plus u f prime of 0 plus u squared over 2 f double prime of 0, and so on. And the only integrals I now need to do is the Gaussian. That's a constant, doesn't matter. Gaussian times one factor of u, Gaussian times two factors of u, and so on. Is that okay? So let's do it. So first of all, Gaussian times one factor of u. I don't know what it is. Actually, I do, but you don't need to. It's just some constant. Times the function at 0. That means what? That means psi at x. Right? At u equals 0. Okay? The next term has a single factor of u times a Gaussian, 0. Right? The next term has a u squared times the Gaussian. Now, an extra factor of u squared will give you a factor of epsilon, because the typical value of u squared is epsilon. You can make that formal by a change of variables and so on. So the next term will give you a factor of epsilon times the second derivative. I say a factor of order epsilon. You do it more carefully, you figure out the prefactor, numerical. There's a numerical prefactor. And if you, that prefactor is a 2, and if you include this a half, you include this a half, you get a quarter. All right, now, the fact that it's a quarter, you can do that. That's just arithmetic, or you look up a table. Okay? With the same, compared to the same integral without the factor of u squared. Now we are almost done. So let me go over here. So psi of x and t is equal to the prefactor, because I'm talking about small t. So I can expand that factor as IV of x t over h bar. I forget about the t squared term. That exponential, I just expand e to the x is 1 plus x. Okay? Then what I have is a factor of nc psi x0 plus 1/4 epsilon. Now, what is epsilon? I have to write down what is epsilon. 2t h bar over im. All right? Oh, by the way, if I had kept on more terms, I would get epsilon squared and epsilon cubed, which would give me t squared, t cubed, and so on. And I'm doing only to first order in t. So I'm almost done. First of all, look at this equation for t exactly equal to 0. So that's 1. That term vanishes because of the t. So psi of x and 0 must be equal to this constant times psi of x and 0. That tells you that that constant must be 1. Right? That's actually how you determine the normalization constant. Okay? So first of all, I erase this. That just makes sure that at t exactly equal to 0, I get the right answer. Now I just multiply it out and sort out the different powers of t. So 0 power is just psi of x and 0. And then 1 power of t is the following. Minus IV of x over h bar, this one times this one. And then there is this one times this one, plus 1/2 t over h bar im psi double prime of x and 0. All right? Move this term over here to the left. So you have psi of x and t minus psi of x and 0 divided by t is, let me write this term first, h bar over I. Oh, so there's no t. This t I have already taken out. H bar over I, 1 over 2m, psi double prime. And then this one is minus IV over h bar, psi of x and 0. Are you with me? So what's the left-hand side? because t is so small. The left-hand side is just the time derivative of psi, right? And let me multiply by I h bar. So what do you have? The first term is then minus h bar squared over 2m. The second term is v. Got it? So you get Schrödinger's equation, and what was the starting point? The starting point is that the propagation from here to here is e to the is over h bar. That is the only thing I have started with, and you have Schrödinger's equation. All right? So I think I will skip one little short topic, and I hope I have given you a taste of how quite a number of different things are tied together when you try to express everything in terms of the action, which is one of the nicest objects in theoretical physics. Okay, so any questions? We have a few more minutes. Oh, I have a half hour, huh?
You can talk about GR now.
Huh?
You can talk about generalized relativity.
Well, let's pause first. Any questions at this point?
We start with the deviation of action to be 0. But that do not tell us the action should be the least or any extreme number.
Okay.
Then that one only tells us that we should be locally flat.
Yeah, good question.
And I also know that Fermat principle do not tell us any light must propagate along the least time path, but the extreme path.
Answer to both questions are basically the same. Now, I said principle of least action. I have actually only used the fact that the action is extremum. I haven't proved that it is minimum. So let's prove it. Suppose you have this path. Well, this is not 100% proof, but at least I can show that it's not the maximum. Because you find a path where the action is extremum, I can always make the action larger. Okay? So it's a maximum. That's not possible, right? How do I make it larger? I consider this path, which stays very close, but goes up and down. Okay? Now, if it stays very close, the potential energy is the same, right? So the potential term is the same. I take the limit where it goes to 0. But the kinetic term is much larger. The red line, if you look at x dot squared, is much larger, right? So I have made the action larger. I have found a path where the action is larger. So it's not a maximum, okay? Partial answer. Fermat's principle, the same. You know, if you have a geometric path that goes like this, I can always go like this, right? You can always find a path that takes longer time. All right? The other questions?
The t squared, t cubed, they are so small, and in the sense that perhaps it is not much that the prime time constant. But
what constant?
Prime time constant.
No, I didn't say it was
because
time constant.
you said that we can treat t as a very small number, but we can't treat h bar as a very small number because we're doing quantum mechanics.
Yeah.
But I mean, Planck constant is already very small.
No, I never talk about Planck constant. Think about, suppose I'm talking about hydrogen atom, right? So when you solve hydrogen atom, you never say h bar is small. Okay, so I don't say h bar is small. But I take everything to first order in t. Because ultimately, I want to calculate this where t is going to 0. So I calculate only to first order in t. That's why I dropped the t squared and t cubed without making any statement about h bar. Okay?
So what I want to point out is that, what I want to ask is that, what is the limitation of the Schr&ouml equation if, here in this case?
Well, if the classical mechanics is given by the Newtonian form, that the classical Lagrangian is 1/2 mx dot squared minus the potential, then the corresponding quantum form is this. Now, you can say, what if the classical Lagrangian does not take that form? For example, suppose you have a magnetic field. If there is a magnetic field, then the classical action is not like this. There is a term that goes like V dot A, right? Then what do? You have to go through this calculation, including the V dot A term. Okay? And that will give you the Schrödinger equation in the presence of A. So that is actually just mathematics. But you have to understand the concept that you put whatever classical action you have, erased, up here. You say that the propagator for a short segment is e to the is over h bar. That is the statement. What s you use depending on what you assume about the classical mechanics. All right? Oh, but that actually throws up an interesting problem, which I will mention, but I will not give you the solution to. Suppose there's a magnetic field. The action involves A. You put it in, the quantum mechanics will involve A in the final answer. So Schrödinger equation, A appears, right? In fact, I will tell you how A appears. I won't derive it, but it goes like this. It goes as I h bar d psi dt is minus h bar squared over 2m. Gradient, now I'm not sure about the sign. I think it's a minus. Something like this. Probably h bar here. Something like this, all right? I could be wrong by a sign with that factor. But the point is, A appears. Now, you all learned in classical EM that A is not unique, right? You can change it by a gradient. So for the same experiment that you are talking about, you use one set of A and solve that equation. You use another set of A and solve that equation. You have better guarantee that the answer in terms of the energy levels, the probability density, anything that you can measure must be the same, whether you use this set of A or that set of A. Doesn't look very obvious, right? So that is a deep question that I leave you with. Unlike classical mechanics, because classical mechanics, you can always express your law of motion in terms of B without the A, because you are talking about Lorentz force law. I don't have to talk about the A, right? So that is a deep question. I won't answer it, okay?
I think at the beginning of the talk, you mentioned that there are two levels of understanding philosophy of the principle of this action. So what is the second particular level of understanding?
Oh, I didn't say that.
How to understand the philosophy? I mean, it is difficult to imagine that the particle, the system itself, has already done all the path integrals and compared.
Okay, to that question, I thought I had given the answer. And that is, actually, every path is equally possible if you look at a single quantum mechanical path. It's only for the so-called classical paths or the neighboring paths have constructive interference. It's not that let's say the electron doesn't go along other paths. It does, but it's destructive interference. That's why you don't see it. That is the quantum point of view. Right? Okay, 5 more minutes about 1/2 of general relativity. Now, I told you in special relativity, the key idea is that there is a thing called the invariant interval. That's the thing which is the same to every observer. And with that statement, everything about special relativity follows. Let me write it in the following way, that in a differential way. That's just a change of notation. And let me call x mu to be x, y, z, t, where mu is 1, 2, 3, 4. So this can be written as dx mu, dx nu, eta mu nu, where eta is the diagonal matrix 1, 1, 1, minus 1. Right? So that's just a, you may say, clumsy way of remembering that minus sign to express a new invariant object. General relativity consists of the following. It says that the invariant distance between 2 points is given by a slightly more general form. It says it is actually the invariant object is a general quadratic in the displacements. So that means these coefficients are arbitrary, not necessarily given by this, just some arbitrary object which depends on position. And that statement defines what's called Riemann geometry, just tells you that distances are measured by a generalized Pythagoras theorem involving the most general quadratic object you can think of. So what is the action in this case? Just following what we did before. What did we do before? We change the sign of this, take the square root, and multiply by minus m. Remember? So we say now that the action is minus m, the square root of minus g mu nu dx mu dx nu. With that formula, we have solved half of general relativity. Because general relativity consists of 2 stories. One is, given the curvature of space-time, how do particles move? That is sort of like the Lorentz force law in EM. Given the EM fields, how do the charged particles move? The other half is, I tell you how the particles move, you tell me the curvature of space-time. That is like Maxwell's equations. You tell me rho and j, I want to find E and B, okay? So here I only tell you about the first half, the easier half, that if I tell you the curvature of space-time, namely little g, which is called a metric, how do the particles move? Well, it moves to make this thing a minimum. The rest is just algebra. One more step. I won't do the rest of the algebra, but just one more step. You know, how do I do this integral? Have you ever seen an integral with 2 d's living inside a square root? You don't even know what it means, maybe. Easy enough. Divide by some ds and multiply by ds. That's certainly okay, right? Because I have 2 ds inside the square root. Now that looks like an ordinary integral. S is called a path parameter. So if the particle goes like this, you just arbitrarily say this point is s equal to 1, this point is s equal to 2, this is 2.1, this is 3, and so on. You just label every point on the path by a progressive parameter s. So this, no matter how complicated, is a function of s, right, inside the square root, and you're doing an integral with respect to s. So at least you understand what the symbols mean. Oh, don't confuse the little s, which is a path integral, with capital S, which is the action, okay? So the law of motion is that this is equal to, the change in s is equal to 0. All right? I leave it as an exercise for you to write out what is a differential equation. It's not hard. It's not hard. You just have to be a little bit careful. Okay? It's just algebra, nothing fancy. And that is what's called the geodesic equation. That tells you how point particle moves in curved space-time. And for those of you who have taken relativity, that gives you things like the bending of light. That gives you things like the advance of perihelion of Mercury. Or, well, advance of perihelion is just a consequence of this thing, nothing more. Okay? So you see how powerful this concept of least action is, how it ties together quite a number of problems that you see in different courses in physics, in relativity, in advanced mechanics, in electrostatics, in electrodynamics, in general relativity, in special relativity, and so on. All right?
So does anything does not have least action relativity?
At a fundamental level, no. If you talk about elementary particles, because we believe everything is built up from elementary particles, right? From the theory is the action. So the quest is actually to find out the correct action, and the rest is just calculation. Of course, at the moment, we don't have the correct theory if you involve gravity together with quantum mechanics. We don't know how to write the proper action. That leads to a finite answer, okay, with the high order corrections. So if you want to study particle physics, the first thing you write down is the action. That defines what the theory is. Then the rest is just calculating the consequences.
Is it really necessary for the action to be an invariant? I mean, for example, in the relativistic part, you mentioned that S should be an invariant. So you simply put a square root on top of the dg squared minus something. But, well, I believe in you, that's of course true. But for some problems or in some other systems, can it be not an invariant, but for different S, they all decrease to the same extent when you change to another coordinate or you use another point of view to calculate X. Maybe they all decreases. So the maximum, the minimum is still that one. I mean that part. Is it possible? Are there any practical examples showing that the action is not an invariant?
Okay, good question. Let me try to rephrase this slightly, okay? I draw a schematic. Now, let me plot the action. This is a schematic coordinate, different paths. So suppose it goes like this. Then the principle of least action says that is the solution. Now, another observer must give the same solution. So it must give the same maximum. So you are asking whether a different observer can calculate this S, for example, or even this S, so long as they have the same minimum, right? At the level of classical physics, that's not ruled out. Okay? So when I say S has to be invariant, exactly the same, that is, if I go to another coordinate system, another observer, it still stays as a blue curve. That is a sufficient condition to get the right answer. You are saying it's not a necessary condition. You are correct in classical physics. But if you go to quantum mechanics, if you believe that quantum mechanics is given by e to the is over h bar, you are sampling all paths and their s values. You are not restricting yourself to the single path with minimum s. And you still must get the same answer. All right? Then I think you are pretty close to saying that it has to be the same. Now, maybe there is still some wiggle room because you are not measuring s by itself. It's s appearing in the integral and so on. Maybe there's some clever way to have some freedom. But you can see that the freedom will be very restricted. And I have never seen an example where you can do it. Okay? So at the back, there is always quantum mechanics. You want to get the quantum mechanics to be also invariant. There is not much that you can fiddle with. Okay? Quantum mechanics does not only sample the path with minimum s, it samples all paths. Any other questions?
If even more, the amplitude are the same, but the quantum mechanics allows the path that is not causally related.
I don't know the answer offhand.
Is it any simple proof that delta S won't goes by like this, such that there is a force, delta S is 0, but it is not a minimum or a maximum? Just a pattern.
In fact, I can rephrase the question slightly in the following sense. How do you know there's only one single local minimum? I'm not even talking about inflection. How about a curve that goes a minimum here and a minimum here? In that case, both are allowed classical solutions. Now, that's because, you see, normally you are familiar with classical problems where I give you two initial conditions. Then, of course, there's only one unique answer. But if I give you one initial condition and one final condition, there are situations where there may be more than one classical answer, and you would find more than one solution, more than one minimum. And the proof and the result, I believe, is the following. If you talk about time intervals that are not too large, then there's only one solution. But if you talk about large intervals, it is possible to have multiple solutions. But that has nothing to do with least action principle, because I just give you an initial condition and a final condition. I ask you to solve Newton's equation and find whether or not it's a solution. In some cases, you will find two or three. Right? So that has nothing to do with least action. And what I have proved is that any time you find a Newtonian solution, that will be a local minimum. Oh, just as in Fermat's principle. Mirror here, light propagates from here to here. There are two solutions. One is to go directly, the other is to reflect once. Right? Two solutions.
We just derived us the Schrödinger equation. But I think in the basic quantum mechanics course, my professor, I think it's not here, she told us that this equation cannot be derived from evidence.
That cannot be right for what?
It cannot be derived from evidence. So it's just right. Schrödinger just
No, it just means that to get quantum mechanics, you have to assume something. So either you assume Schrödinger's equation directly, or you assume that the propagator from one point to another is e to the is over h bar. That I cannot derive. Okay? I have made that plausible by starting with a plane wave cosine kx minus omega t. Okay? I have made that plausible, but that's not a proof. So you must make a jump. You must assume something. And the only thing is whether what you assume looks natural, looks pretty, looks simple. Right? And I think to say that it is e to the is over h bar looks much more natural, because as I have shown today, it comes just from kx minus omega t, the phase argument in the plane wave. Right? So it's an assumption, but I hope it's a more natural assumption.
Your quantum version of the exact
Yes. That is one of the great discoveries by people like Feynman. And you have a path that travels backward in time. Electron traveling backward in time is actually a positron traveling forward in time. So if you draw a diagram, what's called a Feynman diagram that looks like this, a photon, and you have an electron traveling backward in time and then going forward in time. That actually describes a photon becoming a positron going that way. Okay? So particle creation and annihilation can be described by the antiparticle going backwards in time.
It seems that this principle of interaction is so fundamental that you can put everything into the correct action right at all. So what is the current bottleneck that why physicists currently not find a solution that you can combine gravity with quantum mechanics? What is the bottleneck?
Okay.
The practical.
Now, you know that suppose you write down a quantum theory. There's a simple term which you call H0, and then there's a correction term. Say epsilon H1, you do perturbation theory, right? Have you learned perturbation theory? Huh?
I'm not major in physics, so I haven't.
Well, if there are interaction terms, the way you deal with it is to calculate in perturbation theory, for which you have to sum over all intermediate states. There is an infinite number of intermediate states. And for any action that you write down, there's the danger that that sum becomes infinite. That is not necessarily so bad, because some infinities can be cured. You can write it as infinity over infinity or infinity minus infinity and handle it in such a clever way that you get a finite, well-defined answer. That's called renormalization. Quantum electrodynamics, the theory of electrons and photons, is exactly in that category. But the moment you include gravity, then the infinities cannot be cured. So the quantum corrections are divergent. All right? So the classical theory is okay. You can write down a classical theory. You seek the minimum of S that gives you well-defined equations. May or may not be physically correct, that you have to check with experiment. Okay? But at least it gives you a well-defined theory. But if you look at the quantum corrections, then when you include gravity, the theory becomes divergent. And divergent in such a bad way, it cannot be cured. That's the problem. Okay?
Professor, you just said Schrödinger's equation and the leaf action is basically the same thing. You just start from one thing and you can get to the other. But I think when you start from the leaf principle, leaf action principle, you use some approximation in your derivation to get a Schrödinger's equation. So basically, shouldn't there be some very minimum deviation between the Schrödinger's equation and the minimum?
No. The only approximation I have made is that I take first order in t. And all I do at the end, I take t go to 0. I take the time derivative of psi with respect to t. So it is totally legitimate to throw away t squared and so on. No approximation.
But in quantum mechanics, at time you cannot treat it as continuous. They are discrete. Just like
discrete point.
At time interval.
No. If you write down Schrödinger's equation, t is a continuous variable. Just like any old partial differential equation. T is a continuous variable.
But energy is.
But the allowed energies, when you look for stationary states subject to certain boundary conditions, then the allowed energies are discrete. That's okay. Right? That's okay. That's not the same as saying that T is discrete.
I think in the propagator of wave function, the true observable is the propagator propagating from, for example, x1 to x2 minus the propagation from x2 to x1. That's the true observable. So referring to that causality question, I think as long as those probability of the wave function going outside the light cone is cancelled out by the wave function propagating into the light cone, as long as those two cancel out, I think the action is allowed to sample outside the light cone.
Depending what you mean by the propagator. Actually, there are a number of propagators. You know, G plus, G minus, G retarded, Feynman propagator, depending on how you go over the poles, right? And depending on which one you are talking about, okay? So if you go to momentum space, it's basically 1 over 4 vector k squared plus or minus m squared. And there are certain poles. And when you go do the Fourier transform, depending on how you go over the poles, defines which propagator you are talking about. The retarded one, the advanced one, the Feynman one, and so on. And I think the answer depends on which one you're talking about. Yeah. So if you go home and chew over everything I've talked about, all the little steps that I have skipped over, I think you would learn quite a bit of theoretical physics. Right? But I think the concepts are easy. Okay, so that's it.